solid earth and ice temperature profiles for Greenland. And today I will shortly present you the analysis of the GHF geothermal heat flow observations. So geothermal heat flow affects the basic conditions, which is so it's important to consider this when looking at the coupling of the solid earth and cryosphere. And for Greenland, we have the problem that we have a large area with highly uneven distributed observations, as seen here. We have quite many observations at the coast, but just very few in the inland part, especially where we have ice coverage. But for getting information from these points for whole of Greenland, we need to be confident on the given observations we have. So that is the first part I will present you. And in the second part, we try to find a possibility to infer from a few observations to whole of the area, considering that we here still get some structures and try to get lower uncertainties in these areas. So first we tested the agreement between the solid earth models and heat flow observations by fitting the temperature profiles and heat flow observations with a 1D stationary heat flow equation, which basically is this equation where we have temperature at the LAB and at the surface, or heat flow, and the depth of the LAB and the MOHO, and also some unknown thermal parameters. And we first adjust these thermal parameters to fit the LAB temperature by using a Bayesian inversion with Monte Carlo Markov chain. So as input, we have our heat flow observations, the MOHO depth, and the LAB depth. These come from a model from Agnes Wansing. And with this, we adjust these thermal parameters. And to look at the reliability, we can take a look at the fit of the inversion, which basically is that we compare the calculated LAB temperature with a model to the given LAB temperature and look whether it lies in an uncertainty range. We defined an uncertainty of 100 Kelvin due to the uncertainties in our models. And what we now get is a map for the reliability of the inversion, of the deviation of the LAB temperature, which is shown here, where we have most of the points quite close to zero, so they are reliable within our approach. And one point that's quite striking, it's the Angra point, which is quite far away from our initial assumed LAB temperature. So I guess we're 250 Kelvin higher. So we could say that this point is quite has a low reliability, which then means that the LAB is inconsistent with our heat flow observations and also the given ranges for our parameters. And since these ranges and our models assume regional structures, we could also assume that the heat flow points that have a low reliability could represent more local structures. So for just interpolating, for example, we would get more regional structures, but we then wanted to find a possibility to include the points of lower reliability to get information on a local scale and still include these points. To do so, we tested the spatial influence with a simple Kriging interpolation. So I guess you know Kriging, but we have our known values at our heat flow observation points and their mean value, and a grid or the map of Greenland where we try to interpolate to as our unknown values. And this is also influenced by a certain weight, which depends on the point distance, which I will call length scale, and a semi-variogram, which can be seen here, where we have the semi-variance or dissimilarity of our points and the point distance. So we got one single point, for example, and go further with the distance. And if we plot our experimental data, we get at some point to a threshold of our dissimilarity, and this marks where we have the last influenced point from our initial point at distance 0. If we now have sparse data, we get the problem that the kriging or semi-variance still wants to fit a model through our points, which then means that large ranges or large length scales are assumed. So if we do this with Greenland, we get the problem that we get length scales of 600 kilometers for the heat flow. But if we, for example, do the same thing with the higher covered regions of Scandinavia and North America, we get length scales that go down to 125 kilometers, which might be more I forgot the word. More reasonable for heat flow. So, but due to the uncertainties with the kriging, we can't just go down with the length scales, but we can test a conditional simulation that can simulate these smaller length scales. So this is just an example, not the Greenland area, to explain the conditional simulation. So here we get our observation points and first do a normal kriging interpolation, which results in our kriging estimator. For Greenland, this would be in the length scale of 600 kilometers. Then we perform just random distributed field simulation. Get some random field with a small length scale. For Greenland, this will be the 125 kilometers. And then we can take the values from our simulated field at the location of our observation points and can perform again a kriging interpolation, but this time from our simulated field with the large length scale. So basically we here have a regional effect and again a regional effect, and here more like a local effect. And if we subtract a regional effect from our simulated field, we just get the variance of our kriging of our simulated field and can add this to our initial regional structure of our investigation area and get the conditional simulation. So we here kind of get the regional structures of our investigation area, for example, Greenland, but added some small scale changes with a small length scale. This is just, if we perform this one time, we just get one realization. We can't say that this is the true realization, but in case of investigating the influence of ice sheet dynamics, for example, it's important to know whether we have a large hot structure or just a small point. So if we add this to Greenland, we also tested the influence of our low reliability point N group. So if we just do this with our large length scale, we get a code model for Greenland. If we exclude the N group point, we then include the N group point. In central Greenland, we get this high heat flow area, so we get kind of a warm model for Greenland. We get one realization of our conditional simulation. We can simulate more local structures. And for example, the N group point, if we include it, has just a local effect. But to verify this, we would need maybe some more points, but the S group point is in planning. So you hopefully get some information on that. Yeah. So to conclude, we see that the N group point has a large influence on our heat flow distribution due to the sparseness of the data, which also can be seen in previous models, for example, from Kogan, where we also get a code model without the N group point and a warmer model with the N group point. This is based on machine learning. So in comparison to our final result, we see that it's kind of in between. It's not that warm as the warm model, but still got some influence of the N group point. And one part of our next steps is that we want to combine our heat flow model with the SMOS ice sheet profiles to perform the coupling. So yeah, thanks for your attention.
Okay, thank you very much, Judith. Is there a quick question? Otherwise, I would ask, can you include the uncertainties of the heat flow measurements themselves? Or is it already considered?
Right now they're not considered. So we get our uncertainty of 100 Kelvin. This kind of includes the uncertainty of our input models, where we still have, we also didn't include the uncertainties of our MOHO and LAB depth directly, but we assume that the 100 Kelvin covers a wider range if there are some uncertainties.
Okay. Yeah, thank you. Great.
Maybe it's possible to include it directly, but yeah.
Yeah, you still have some time left.
Yeah,
actually.
just started, yeah.
Okay, thank you very much. Okay, so we can go now to Marion and your presentation on ice sheet temperature in Antarctica from satellite observation by using Bayesian approach and temperature emulator.
Okay, could you see my screen?
Yes, but
Yes.
it's not in the presentation mode.
Okay, change the mode. Better like this?
Yes, perfect. Thank you.
Okay. And my pointer, so no, maybe not. I don't know. So, hello everyone. Thanks for giving me the opportunity to present my work with you. And so I present to you the work about the ice sheet temperature in Antarctica from satellite observation. So the idea is we know that ice temperature is essential to understand the Antarctic ice sheet evolution, and mainly because of its interaction with the ice flow. But the problem is ice temperature is only provided by few borehole and glaciological models. So on the map, we can see on the right map, we can see some location with temperature measurement from the top to the bottom of ice sheet. So we have 9 sites, so it's very few with respect to the size of Antarctica. And with the SMOS satellite, we have a new opportunity. This is a satellite launched in 2009 with a new instrument. This is a microwave radiometer 1.4 gigahertz. And we perform several analyses to understand which kind of information we can obtain with this frequency above over Antarctica. And we found that the advantage of this frequency is to this sensitivity to the ice temperature several hundred meters in depth. So that means for the first time, we have the possibility to reach information about ice sheet temperature in depth from satellite. So the objective is to associate the SMOS observation with a glaciological model to retrieve the ice temperature profile. So what is the method that we use is based on 3 main tools. The first one is a temperature profile emulator. It's based on the 3-dimensional ice sheet model, and it takes as an input several glaciological parameters. From this emulator, we obtain some temperature profile that we use in a snow emission model to reproduce the SMOS signal. So we simulate brightness temperature. And then we compare this simulate brightness temperature with the SMOS observation by the means of minimization method. So this method is a Bayesian approach. And we run this for each SMOS pixel, and that means for each SMOS pixel, we have a retrieve temperature profile. So in the follow, I present to you this temperature emulator, then the Bayesian approach, and after we discuss the result and perspective. So here I present to you the temperature profile emulator. So the objective is when we need a temperature profile, not run each time all the ice sheet model, but find a more easy way to use it. So for that, we develop a temperature profile emulator based on the neural network. So this emulator is based on the Grizzly three-dimensional ice sheet model and take as an input surface temperature, ice thickness, geothermal flux, accumulation, etc. And is forced with past surface temperature over 25,000 years. So the DNA is based on 20 run from Grizzly with various geothermal flux map. And so this work is led by Catherine Rich, which is with us today. So I don't want to enter more in detail because I don't know. I'm just a user of this emulator. But if you have some question, you can ask to Catherine also. So from the smooth point of view, this simulator based on the neuronal network is very easy to use, very fast. And we can use it for everywhere we have ice thickness above 1,000 meters thick. So now I present to you the Bayesian approach that we have. So we have four main geophysical parameters. The first one is ice thickness. We consider that we well know this parameter. We keep fixed over Antarctica. And we have three parameters: the surface temperature, snow accumulation, and geothermal heat flux. So for surface temperature and snow accumulation, we have as a prior distribution and normal distribution, and we take a data set from literature with the standard deviation associated to this data set. But for geothermal flux, it's much more complicated because, as you know, we have a large uncertainties above Antarctica, and we have several data sets with sometimes large difference. So to take into consideration each data set with all the possibility, we define as a prior distribution a multi-Gaussian distribution. Like this, each data set is big in the distribution. So we can see the list of the data sets that I use on the right side. So this is a Bayesian approach. So we search the probability to each node to predict the smooth observation, and so that means at the end we have a set of equiprobable temperature profiles. So I show you the results as we have at Domesday location above the plateau. So on the right, we can see the posterior distribution. No, on the left, we can see the posterior distribution for the three parameters. In blue is for the geothermal heat flux, orange for the snow accumulation, and green for the surface temperature, and the red one is for the brightness temperature. So the vertical line, solid line are for the a priori values that we put in as an input of the algorithm, and the dashed line is the maximum likelihood, so the value that we obtain at the output of the algorithm. So for example, for the geothermal flux distribution, we can see that from the smooth point of view, we have a value around 50, which is higher than the 4 value proposed by 4 other datasets. In the middle, we can see all the possible temperature profile that we obtain for this location in black. And in blue, this is the measure that we have in this location, and orange, this is the maximum likelihood that we obtain. And then on the right, we have the difference between observed and retrieved ice temperature. So we can see that we have a good agreement with in situ measurement and retrieved ice temperature, but it's better in the upper part above 1,500 meters because we are different lower than 1 Kelvin, and the difference increase with the depth. So it's expected because we know that the most sensitivity is higher in the upper part of the ice sheet, and we lose sensitivity when we go deeper. So it's we have to keep this in mind. So this is for Domesday, and we can do the same for the 8 other sites where we have observations. So here I show you the 5 sites we have over the plateau. And so it's blue is the estimation with the standard deviation, and black is the observation. So we can see in the 5 SAT, we have a very good agreement between measure and estimation, with a mean difference lower than 1.6 Kelvin. But in some place, in some place, yeah, each time we can see that we have a larger standard deviation with close to the bottom. So around 3, 4 for Dome C or Dome Fuji, for example. So this is over the plateau, but we have also 4 sites in the West Antarctic and close to the coast. And the temperature profile is slightly different, but also in this case, we are a good agreement with in situ measurement. So since it's work with this location, we can apply the retrieval over the whole Antarctica. And so here I show you the results that we have. So on the top, you can see a temperature map for 4 different depths. So surface 500, 1,500, 2,500 in depth. And so everywhere we have ice thickness higher than 1,000 meters. And in the bottom, we have the standard deviation for each depth. So in the same, we can see that we have a standard deviation lower in the upper part, and in some places it's increased with the depth. So now we can check the quality of this retrieval. And so for that, we focus on the brightness temperature. And on the left map, we can see the simulated brightness temperature from the retrieved ice temperature profile. And in the middle, we compute the difference between simulate and smooth observation. And we can see that over the plateau, the difference is very low, lower than 1 Kelvin. And that means we have a good quality in this place, but in the West Antarctica, difference are higher than 5 Kelvin. It's not very good. And this suggests that we have some trouble with the ice emission modeling because the ice dynamic in this place is really different from the plateau. And so we know that it's more difficult to reproduce the small signal in this place. So we decide to build a quality flag, and we can see this flag on the right map. So we say that if the difference is lower than 1 Kelvin, it's green, it's okay. It's lower than 2, it's okay, we can use it, but it's upper than 2 Kelvin, we have to take care in this place, in the reliability of this place. So just to summarize, we have an algorithm based on the Bayesian approach to combine smooth observation and a glaciological model. We are able to run it over the validity area where ice thickness is higher 1,000 meters on the new 3-dimensional emulator. And at the end, we have the ice temperature, standard deviation, and a quality flag. So the next step is to improve the electromagnetic modeling to improve the result over the West Antarctica, apply this methodology to Greenland ice sheet, and also to understand if this work could help for inferring geothermal flux or not. And these 3 points are objective in the new ESA project in progress. And for the last point, we are in collaboration with Marion, Judith, and Jörg. And this is a work in progress, so we have to think about how provide information from both to the work to the retrieval of geothermal flux. So I show you just some idea. Here we have on the left, you have the posterior distribution of geothermal flux at Dome C. So in blue and in black, we have the a priori value, and dashed line is the maximum likelihood that we have. The problem is MOS is sensitive to the ice temperature and not directly to the geothermal flux. So that means in case we have melting at the bottom, so we have a warm base, SMOS can't give an information about geothermal flux. So, and we have a kind of maximum value of geothermal flux from the SMOS point of view. So this is the histogram that we can show in the middle figure, central middle. And so the kind of information that we can obtain from SMOS in this case is to say, okay, SMOS can say if we are in cold base or if we are in warm base. So here, for example, SMOS says that in 15% case are cold base. So we can say, okay, SMOS Dome C is a warm base place. The second information that we can provide is also the distribution of basal temperature, because we have many profiles at this place, and so we can give this distribution. So this is for one location, but we can also provide some kind of map, so we can provide the basal temperature and also the uncertainty about this temperature. So we can see this on the left map. On the right map, we can also propose a kind of indicator to say if you are in cold base or in warm base. We can also give the percentile of warm and cold base from the SMOS point of view. So all of this is the kind of information that we can provide with the algorithm. So it's a work in progress. We have to discuss with Marion and Judith to see how to do that. And that's it. Thank you. If you have questions.
Thank you very much, Marion. That was interesting. Are there some questions? I think you can just unmute yourself. I'm not sure if you can. You can also raise your hand. Also on YouTube Teams.
Yeah, thanks a lot. It was very interesting. I was a bit curious about the basal melting and how much heat, not only the wet-based areas as such, but how much heat that could be removed by the melting, by the subglacial hydrology. Do you have any ideas about how that will impact your profiles and how you can encounter for that?
I can answer, Marion, if you want. I can answer from the ice sheet model point. You can have a typical 1 millimeter per year of melting, and the feedback is that when you have melting at the base, then you have a downward velocity that is that brings cold from the upper layers, and it's a negative feedbacks. And in the emulator, there is no real impact of the amount of basal melting. Or it is in the 3D model. There is an impact, but I'm not sure we can detect it in the emulator, because one point is that we tried to give to the emulator only something that can be observed, and we cannot observe the basal melting. So it's part of the difficulty that we only prescribe surface temperature, thickness, accumulation rate, and the only thing we don't prescribe is, or we don't know, is geothermal flux. And the basal melting is, we could develop an emulator with that, but then the problem of observing it to feed the Bayesian procedure would be complicated.
Yes, understood. Thanks a lot.
So you are now using these 6 different heat flow models with a multi-Gaussian, I guess.
Yeah.
Are these already included in the results that you are showing here in the last slide, for example?
I apply only on the in-situ measurement site, not yet over the whole Antarctic, because it takes more time. So I have to to do other change before to rerun one timer.
Yeah. Okay. Yeah. Yeah, that would be interesting to see how that changes.
Yeah, I think for us it could be good.
And do you also see an improvement with the individual ice sheet profiles with using these multi-Gaussian?
Not really, because before I use the mean of the 6 value, there is no huge difference. It's usually better, but very slightly better. But it's not. But at least now we know what we put as an input. This makes sense because we put the direct number, not the mean of. We don't know why.
Yeah.
So for me, from a physical point of view, it's more logical and more proper, more clean.
Yeah, definitely. Also, maybe there are too many heat flow models now. I think 6 is a lot.
I think it's a lot. So
easily remove the older ones.
Yeah. If you can advise me for which database it's better to use, tell me. I can remove some older ones.
Yeah, yeah. I can do that. I think removing just the last or the oldest ones, the oldest 2 ones or so, which have already been replaced with new data, but the same method.
Okay.
Would be already.
Okay, so it will be better.
Yeah.
I think the question is more to have independent maps, maybe classified as methods to obtain them.
Yes.
Including you can enlarge when free maps comes from magnetic measurement. You maybe can enlarge the uncertainty, but for the Bayesian approach, it's rather important that they are independent.
Yes. Are there more questions? Okay, I don't think so. Then thank you again, Judith and Marion, for giving the talks. Yeah, and I hope to see you again for the next seminar in July.
Yeah.
I will